Welcome back, future oceanographers. Just 1 minute, I'm finishing up an experiment that I think you're going to be able to try at home. It should be something you I don't think this is something you should try at home. So we're just going to set this aside for now. And let's talk about something else. Okay. Anyhow, last time I left you, we started talking about currents. And I said, first we're going to tackle these thermohaline currents, right? Remember me showing you this figure? These are these massive global circulation currents, and they're driven by density differences. So the first thing I want to do is just really quickly talk about density. What is density? What do I mean by that? And how does it drive currents? Well, simply put, density is the mass of something in a given volume. Well, what does that mean? Well, we'll come back to the calculations a little bit later. But all that means is if I have a certain volume of something, so let's take this volume here. So I have two substances here, right? They're both the same volume. There's about 7 milliliters in each of these. And what density means is how much stuff is in that volume. And while it looks like it's the same, if I take and I put it on the scale here, I take this first one, and I put it over here on the scale, what does that give me? It gives me about 6.6 grams, okay? Great. Now I take this other one, same volume, and I put it on the scale, and that gives me about 9.9, almost 10 grams. So there's quite a bit of difference here between the weights of these two. So what that means is the substance that weighs more is more dense. It has more mass. It has more stuff in that volume. It may look the same, but again, that's really the difference. And by the way, density is what makes stuff float on top of one another. So in our case here, if I take, and I've already created this because I was a little concerned that it might not work while I was doing this on the video, but if you guys can see here, I've created a column. And each one of those substances is a different density. And the higher density is on the bottom. So there's more stuff, okay? So on the bottom we have something like honey, and we have soap, and then actually this pink thing here, my attempt at some food coloring, is just plain water. Then we have some vegetable oil, and on top we have some rubbing alcohol, okay? Also colored a little bit. But you guys can see it stratifies nicely. This is actually something you could try at home. So there's different substances in your house, and if you put them, you got to be careful when you pour them, but they will stratify themselves. And I'll come back to, I will say that term a lot, stratification. And that just means layering, okay? And I'll say it again, but the ocean is stratified this way by density. So there are different densities in the ocean. And what this does for us is this is what drives those massive global currents. So let's go ahead and head back into the office, out of the lab, which is mildly dangerous apparently this time of year, and let's talk more about how these densities affect these global currents. I'll see you back in a bit. And there you have it, this massive global circulation of ocean currents, these thermohaline currents, transferring energy all around the planet, transferring heat based on density differences, based on temperature. Okay, so you guys can see this here. It's amazing. But what do I mean by all this? We've seen what density is. I keep throwing around these terms, density differences and temperature differences and heat and energy. Well, these aren't all interchangeable, right? They're actually very specific. And we're going to go ahead and kind of break these down to see how this works. So the first thing I want to do is I want to talk about the difference between heat and temperature. Because again, these are very different things. So let's start with temperature. You guys are probably more familiar with that. And really that's just a measure of hotness or coldness, right? You take a thermometer, you measure something, and you get a temperature, and you get a number, and that's it. And what that's based on is the average molecular kinetic energy. And that just means how much the atoms or molecules are bouncing around. So if you guys are a fan of Bob Ross, you remember his happy little molecules here. And on the one side, these are both water, same number of molecules, but this one's hot and this one's cold. And you can sort of see here that these molecules of water are bouncing around more, right? They're more excited. and the cold water not so much. And that's the measure of temperature, is just how much those things are bouncing around. Now, heat is a little bit different. Heat is more about the total energy of something. So this is based on the total energy of those molecules. And what this means is if you have two vessels of water and one is 4 times larger than the other and they're at the same temperature, well, there's more heat. There's 4 times more heat stored in the larger vessel. You can also think of it like if you had a mug of hot tea or hot coffee or something that was a really high temperature, and you had a swimming pool that was, I don't know, nice, right? 80 degrees or so, really nice. Well, there's actually more heat in that pool, even though the temperature's less, because there's so much more mass, right? There's more molecules bouncing around. And we use this heat to talk about why water is so special. And so the next term I'm going to define is this heat capacity. And that is specifically the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius, okay? And water has a very large heat capacity. What that means is it can absorb an incredible amount of heat without changing temperature all that much. What that also means, the opposite is the difference in a small amount of water temperature is an incredible amount of energy. So think about it this way. If you're at the beach, nice hot sunny day, and you get up from your chair and start to walk around and that sand is really hot, okay? And the first thing you're gonna do is you're gonna run over and you're gonna run down and you're gonna try and get in the water. Sometimes that doesn't work out so well, but you guys get the idea. So you can look at that as the heat capacity difference between the water and the sand. All right, same amount of energy from the sun, but the temperature change of the water is very minimal, whereas the sand is really high. It does not have as high of a heat capacity. So that's why you can run into the water to cool off. It's not because it doesn't have as much energy going into it, it can just absorb it. So anyhow, what that means again from this is that different substances obviously respond differently, and this will keep coming back to why water is so special. So here's a table here. I don't know how well you can see this, but we'll fix that in a minute. And there's just different substances over here and their heat capacity. And you can see pure water is a heat capacity of 1. Again, I'll come back to the units in a minute, and that's just because the definition was based on that. So it's 1 because that's where we kind of formed everything around. You can see things like silver way up here, a metal, right? Metal gets really hot really fast, has a very low heat capacity. So with these numbers, let's actually kind of jump in here and do one of our first set of calculations and figure out how all this works and how we can figure out specifically the temperature changes and energy influx for different substances. So here's the table I just showed you guys. Hopefully you can see this a little bit better now. And all this is showing you is, over here on the left, we have a bunch of different substances. You'll see water right here. And then this is their heat capacity, right? And we define that as energy, so calories is the energy that it takes to change 1 gram of a substance, right? 1 degree Celsius. So that's specific heat capacity. So heat capacity in general could be any amount of grams and any amount of temperature, and we'll see that here in a minute. And you'll see water sits right here at 1, and that's again because this is based on water. So I'll show you another figure that will kind of explain this. And this is showing the cycle of water. So over here we have ice, in the middle we have liquid water, and we have water vapor or steam. And this is just showing as you move through these phases what happens. So this 1 is because if you take 100 calories, so 100 divided by 100 degrees, you get 1. And that's all this means. It's 1 gram of water at 100 calories, you get 100 degrees, right? That might not seem amazing, but I'll show you here in a little bit why. The first thing before we leave this figure I want to show you is that, okay, so over here on the left, this whole area, right, is 0 degrees, right? We're not changing temperature. So just to go from ice at 0 degrees to water at 0 degrees, that's 80 calories. So almost as many calories as it takes to get from 0 to 100. Again, that's because you're breaking those hydrogen bonds. It takes energy to do that. Now, if you look over here, in this area over here is all steam, and it's all at 100 degrees. And just to go from 100 degrees, not changing, from liquid to water vapor, 540 calories. Almost 5 times as much to change, again, from freezing to boiling water. And now that's because you have to break every single one of those hydrogen bonds, right? They all have to be broken for water to turn into water vapor. Each individual molecule on its own density gets much lower. So that's a lot of energy. So that, again, is why we say that water has an incredibly high heat capacity, which makes it very special for a lot of reasons. All right, So that's great for water. Let's go ahead and let's get rid of this figure and get rid of my doodles here. And let's look at some of these other substances. All right, just to give you an idea of, again, why water is pretty amazing. So let's look at something like granite. All right, so we see granite up here, and it has a heat capacity of 0.20 calories per gram per centimeter, or per degree Celsius. What this means, and now I'm also at this time going to show you how I want to see you guys set up your homeworks. You'll notice again those homework problems, there are various points in there. I will tell you that in every single case, the correct answer is worth one of those points. So if you have a 12-point problem, 11 of those points are something else. That's the show your work part. And I'm going to try and show you each time we do these what I'm looking for, but if you ever have questions, make sure you ask before you turn your homework in, because once it's turned in, I can't really do anything about it if you missed it. So let's see, how do we do this? So let's go ahead and say I want to take granite. So granite, and yes, my handwriting is amazing here, and I want to do 1 gram of that, 1 gram of granite. And I'm going to do the same thing I did with water. I'm going to add 100 calories. Let's see what happens. I'm going to start at 0 degrees Celsius. All right, well, the first thing is I'm going to write down the heat capacity of granite, and that is 0.20. And again, calories per gram degrees Celsius. Always, always write down the units. I guarantee you units, just writing them down is at least one of those points, if not more, in each of these problems. And actually, they're incredibly important. This first problem that you guys have is fairly simple, but it's a really good way to show you why units are so important, because it will help you know whether or not you got the right answer. It's almost like cheating. Anyhow, so I'm going to take this and I'm going to add 100 calories and see what happens. Well, the first thing, and it may seem trivial, is I'm going to take this number and I'm going to multiply it by, 1 gram, because that's how much I have. And some simple algebraic manipulation, the grams cancel, and I'm left with 0.20 calories per degree C. And yes, in this case, it's the same number, but it won't always be 1 gram, so it's important to do that, and yes, I will look for it. All right, so I have 0.20 calories per degree C, and I want to add 100 calories. So I'm going to take my 100 calories, and I'm going to divide by 0.20 calories per degree C, because again, dividing means I can cancel that calorie out, I can cancel that calorie out, I can move degree C to the top, and that leaves me with 100 divided by 0.2, which is 500 degrees C. A lot, right? So this is that sand, right, that you're walking on the beach. This is the reason it gets so hot. So same amount of energy that we added to water that took it from 0 degrees to 100 degrees Celsius takes sand, granite, to 500 degrees Celsius. That's pretty impressive, right? And that's most rock. Let's just say rock, sand, all that stuff is pretty similar. So what else? I'm going to show you one more of these, and I'm not going to write all of this out this time, but let's take a look at silver, right? Metal. And it's 0.06 calories per gram. Well, if I do the same thing and I add 100 calories, right, and I start with 0 degrees Celsius, that's actually going to bring me to about 1,000, well, I'm going to look at my notes here, 670 degrees Celsius, or about 3,000 degrees Fahrenheit. That's a lot, okay? And that's why, you boil water, that's why the pan gets so hot immediately. All right, so metals do not have a high heat capacity. They get hot very quickly, incredibly quickly. So again, just to show you, water is pretty amazing for its ability to absorb heat and again, transfer that heat around the planet. All right, well, you know why water is so important. We see what heat capacity is, why it can hold so much. So let's go, I'm going to try to go start to finish through an example problem so you guys can see exactly what I'm talking about with one of these. So for my example problem, I'm going to use gasoline. Why not? Okay, gasoline with a heat capacity of 0.50 calories per gram per degree C. So if I were to give you a problem, then I would say, okay, you have 3 grams of gasoline, and I want to know what do I want to know? I want to know how many calories it will take to go from 12 degrees to 30 degrees, all right? So the first thing you should do is write all this stuff down. I'm going to give you word problems. You need to pull out this information. Just write it down so you know what you're working with. All right, so the next thing I'll say is, okay, well, I have my knowns. I know that gasoline has a heat capacity of 0.50 calories per gram degrees C. All right, well, I have 3 grams of that. So the first thing I'm going to do is I'm going to multiply that by 3 grams. Okay, my grams cancel. 3 times 0.5 is 1.50, right? Calories per degree C. All right, so I'm looking for calories, so I need to get rid of this temperature part. Well, I know I want to go from 12 to 30, and I'll take 30 minus 12, and that gives me 18, right? I'll cram it in the corner. So 18. So very simply, again, now I take my 1.50. Again, units. Don't drop your units. I will find it. And I'm going to multiply this, because the temperature is on the bottom, by 18 degrees Celsius, right? The temperatures cancel, and that gives me and I'm going to cheat again, 27 calories. All right? So that's how you would go through that. Now, just to point this out, I won't do this every time, but I do want you guys to get this right. My goal in this class is not to trick you. I want you to hit all of these points because they're really important. So, I can't even remember what your homework points are, but let's just, for argument's sake, say this is 4 points. It might only be 3. I don't know. Well, first things first is, in fact, let's change colors here. First things first is the answer is 1 point. That's it. All right. So 3 more points are in here somewhere. Units, right? So units here, carrying your units through all the way, even when you do this, all those units, that's at least going to be 1 point. All right. And that might be a couple since we have, so I would say that's actually 2 points because that's really important. And then setting up these equations, just the fact that you have them set up correctly will be another point, and that would be your 4 points. Now, the reason units are so important is if, you may be able to blaze through this stuff. Again, this isn't really complicated. For some people it might be. This might be very new stuff for you, and if you follow this meticulously through, you'll have no problems. Again, math, I don't like when people say they're not good at math. Well, I'm not good at flying helicopters because I've never flown helicopters. I don't practice, right? This is just practice. If you ever do sports or play a musical instrument, you're not just immediately good at it when you pick it up. You've got to practice. And that's the same thing with math. There's nobody except for like really, really off people that, not off, but really highly specialized, intelligent people that are immediately good at math. For everybody else, myself included, it's a lot of practice. But what that means is if you set up your units, you'll be able to see this. So because I wrote my units down here, I knew I had to multiply by 3 because that had to cancel. Here, I knew I had to multiply by 18. In the previous example, I knew I had to divide. That's because I kept my units. So this is how you need to set it up. Ask questions. Again, you guys have a couple weeks to complete these. Come to office hours. I guess this first one's you have a little bit less time, but there's not as many problems on there as there will be in the future. But ask questions if you have them. So I think that is pretty much it. That is, how we see, specifically how we calculate the heat capacity of different substances and why water is so amazing, why it has that ability to absorb so much heat. So let's go back, let's take this information and go a step further and see how this now moves into actually having these currents move around in this distribution, and what does density have to do with it, and all this other stuff in temperature, right? We haven't really gone into that yet. So let's head back and we'll see what we can do about it. Well, water's special really just because of the way it's constructed. So you can see here is a water molecule. You have 1 big oxygen atom and 2 hydrogen atoms, H2O. And because of the way it's arranged, you end up with what's called a polar molecule. The oxygen side's just a little bit negative, and the hydrogen side's just a little bit positive. And what that means is that these molecules act like little tiny magnets. So when you get a bunch of water molecules together and you have water, right, they form what's called a hydrogen bond. The plus side attracts to the minus side. Sorry, I pointed at the negative. The negative attracts to the plus side, and these start to stick together. Now, this isn't a really, really tough bond. You can think of it. In fact, I've got a little example here. I've got my little Post-it notes. So if you guys have Post-it notes, you know that you can take a Post-it note and pull it apart and stick it back together. Right? It's not super sticky, but it is sticky a bit. So because of that, water has some special properties because of these hydrogen bonds. The first couple, so if you've ever seen like dew in the morning on a spider web, it has 2 interesting properties that allow it to stick to itself and stick to other things, right? And we call these cohesion and adhesion. So cohesion is the ability of water molecules to stick to each other, and adhesion is the tendency for them to stick to other things. And this has a bit to do with that positive and negative, those properties. And if you've ever taken and seen a droplet of water on the table compared to something else, so right here's a droplet of water. It creates that nice dome shape right there. And this is a drop, I think this might be alcohol, like rubbing alcohol. And it's more diffuse, right? It doesn't stick together because it doesn't have that cohesive property. What this also means, other things you might have seen, if you've ever seen bugs walking on the surface, right? They can actually walk on the surface of water. That's surface tension, so that's because of that cohesion. Also, a little more terrifying is if you've ever seen something like this, like a great white shark come out of the water, well, it doesn't immediately break the surface. So I can slow that down a bit. There's a bit of time where there's this film covering whatever animal's coming out of the water, and that's, again, because of those cohesive properties. And that's all because of these hydrogen bonds, right? They stick together. Well, that's really cool, and those are amazing properties of water, but let's use this and kind of go back to why does water have this high heat capacity? Well, again, not a lot of energy to break these bonds, but some. So if you take a look at water and these bonds, so here's a picture of water floating around. Each one of those white bits is a hydrogen bond. Well, they're not always attached. In liquid water, they tend to break and reform and break and reform, and not all of them are sticking together. But again, because it takes energy, what you can do is, again, let's take that sunlight coming down in the ocean. Well, that energy will break those bonds, but not necessarily speed up the water molecules, right? Not necessarily speed up that average kinetic molecular energy. It really has to break all the bonds before things start to speed up. So this is exactly why water can absorb so much energy. So if you guys have ever heard about, numbers surrounding climate change, maybe 2 degrees Celsius, that doesn't seem like a whole lot. On an average day, we fluctuate way more than that. But I hope you're starting to see that 2 degrees Celsius for a surface of the planet that's 71% water, that's a lot of energy. It's an incredible amount. So just remember that when we're talking about these things. All right, so anyhow, this put together now, we see that the water has this high heat capacity. It's able to transfer heat all around the planet, right? So warm tropical water up to the poles and then cold water all around, and it stabilizes our climate. So that answers one question. So we know density, we know heat, but we still haven't really talked about this temperature thing. Why is it that you can see here cold, dense currents, warm, less dense currents? So we already saw, let's take a look at our column here, still kicking, of different density substances forming those layers. Well, it's not just different substances. Again, it can be differences in temperature. And that's what we're going to look at. All right? So the next thing I'm going to show you is why does temperature have anything to do with density? So you guys, I showed you this figure before. It's a little bit bigger now. Over here we have our hot water with the molecules bouncing around, and over here we have our cold. And there's the same number of molecules in both of these. So, the density is the same in each one of these, right? Certain volume, certain number of mass. So we just have to remember that formula for density is mass per volume. Now, you can change the mass, so we kept volume the same in our little example there with different substances, but you can also change you can change the mass and volume both. So let's do this. Let's take an imaginary square that's less than our major volume. So we have this square here, and what do I have in there? I've got 1, 2, 3, 4, and most of 5. So I don't know, 4.8 molecules, let's just say that. Now, that's in hot water. So we have 4.8 per this volume. Now, if I take that box and I move it over to the cold water, and I count the molecules, so the volume hasn't changed, but now I have 1, 2, 3, 4, 5, 6, 7, and change, right? So 4.8 and 7-ish. So we've changed the mass in the same amount of volume just by lowering the temperature. So colder water, all those molecules get closer together and it gets more dense. And warmer water, when it heats up, they start to get excited and they spread apart and it gets less dense. So what you end up with is this. Most substances increase density as temperature decreases. All right, so just remember that. The higher the temperature, the lower the density. Now, water, again, is special, all right? So it's true for liquid water, but only to a point. Above 4 degrees Celsius, or excuse me, below 4 degrees Celsius, the density actually starts going back down. And you can see that in a curve here. So we'll take, this is temperature on the bottom. There's our density. You don't worry about what the units are at this point. But just note that with warmer temperatures, just like we said, density starts low, and as you cool off, density goes up. Then you get to about 4 degrees, all right? And it starts to go back down. Well, that's weird. Most substances don't do that. Why would it do that? Well, this goes back to those hydrogen bonds, okay? So I said in liquid water, you know, things are bouncing around, not all the bonds stick, they're breaking and remaking. Well, once you start getting about 4 degrees Celsius, those bonds start to lock in, all right? And because they actually push the molecules a little further apart, so if you have 2 little water molecules, when they bond, they can actually move a little further apart. So what happens, here's our liquid water with all these little molecules bouncing around. You'll notice some of the bonds aren't there, some are. But you notice here, like there's not a bond, and that water molecule can get a lot closer together. So as the temperature cools down, those molecules slow down and they get closer together. But about 4 degrees, those bonds start setting in. And as it gets colder and colder until you have ice, all the bonds form. And they create this lattice structure, which actually makes each individual molecule further apart from the one next to it. So the density goes down. That, luckily, is why we have ice floating on the ocean. So this is a very general way that the ocean looks. You have cold water on the bottom, warm water above it, just like our density columns, and ice floating on the top. And I said I'd come back to this, and this is one term really important to remember, and that is the ocean is stratified by density, or layered by density. You've got to remember that. So the way this looks, I'm going to give you some general pictures here. We have density zones, and a very basic is a surface, a pycnocline, and a deep zone. Surface zone, you guys can read here, I'm not going to repeat it, is the surface. Deep is deep, right? So warm water at the top, cold water at the bottom, again, less dense, more dense. The pycnocline is the important one, right? This is density increases with depth. This is where that big change occurs. And it looks something like this, okay? So if I show you a figure, density on the bottom, depth on the side here, and this line is representing density. So low density at the top in that surface zone, high density at the bottom, and you can see right here in the middle, that pycnocline, that's the greatest change, right? That's that rapid change in density. You can read a bit more about this, but what this creates are something called water masses. They all have names, read about it. You know, I might ask you a couple questions on it, but basically it just means these differences in the properties, differences in the density of these waters. But that's not it, right? This pycnocline, as we just shown, is based on temperature. So pycnocline, you can also draw a thermocline. So same thing, surface zone, the cline, and the deep zone. And in our case, again, low density, I move my head there, gives you higher temperature, and higher density gives you lower temperature, and we have that same curve. So these two look very similar, just opposite. And this is your thermocline, or temperature cline. All right, pycno just means density. More Greek words, not too important there. But we're talking about thermohaline circulation. So what is haline? Well, what else is the ocean? Well, the ocean's salty. And as it turns out, that salt has an effect on density. The more salt you add, the more dense things get. So what you can also look at is you can think of water that is warm and fresh, so less salt, that means it's not as dense, and cold and salty. And this is just a cork. I mean, you guys can do this at home if you want, and you'll just notice that it floats a little bit higher. In fact, I don't know if anybody's familiar with a place called the Dead Sea, but there are people that can go there. This is over in Israel, and it's so salty, the water's so dense that without any kind of wetsuit or any kind of flotation device, you can just sit there and relax. People can read newspapers and whatnot the whole time. All right, so what this also means, there's a little bit of delay there, but that's all right, is that the pycnocline is also a halocline. So same thing with temperature. You have a rapid change in salinity here. Deep is pretty solid, and the surface zone is not, and it looks the same. Now, what I'll also say, this salinity doesn't change a whole lot in the ocean, all right? Not like temperature. It's primarily temperature driven, but we will see that it changes a bit. So if you put all these together, you get something like this. So here's our density, temperature, and salinity. And again, surface zone at the top, here's all the clines, pycnothermohalocline, and then the deep zone. And so this is what it looks like right next to each other. Now this is approximate. You can see here these density, and actually these numbers don't change a whole lot. You're at 1.024 to 1.028. Temperature, quite a bit. So 0 to 15, that's a pretty big Celsius temperature difference. But salinity, again, doesn't change a whole lot. This is actually, these are kind of extreme down here. Like this is a really low salinity. The average ocean kind of falls right in here-ish, close to 35. So how do we figure this out, right? It's not just approximate. We can actually do this. And some of you have already kind of jumped ahead and looked at your homeworks and tried it. So hopefully this will help explain it a little bit. And there's a figure. There's a figure I've put in the resources section in Blackboard site, and it looks like this. And this is a temperature salinity diagram. So hopefully you guys have pulled this up and you've seen it already. And what this means is it's showing you salinity across the bottom, temperature across the side, okay? And each one of these lines is a line of constant density. So what does that mean? Well, that means if I pick a temperature of 0 and a salinity of, what's that, 34.2 and a half, that gives me A. And it gives me a density of 1.0275 grams per centimeter cubed. Well, if I pick a temperature of about 10 degrees and a salinity of about 35.6, all right, that also gives me the same density. So these are lines of constant density. And what that means is as the salinity goes up, density goes up. As the temperature goes down, density goes up. All right, so that's how you read this figure. So let's do one example, and this should hopefully help you get through your homework problems. So let's pick a temperature of 10 degrees and a salinity of 34.5. And this is what I want to see you guys do. So, you know, these things say show all your work. You should be able to do this. Don't eyeball it. Actually draw it out on these figures, take a photo of it, and submit it with your work. So let's do this. Temperature of 10 degrees, which is right here. And the best thing to do, again, don't eyeball this. Take a ruler and draw a line all the way across. The lines on the other side correspond, so you can draw a nice straight line all the way across. And then a salinity of 34.5. So we're right here. Draw another line straight down, okay? And then where these intersect is going to be your density. And you'll notice this doesn't necessarily fall on one of these lines all the time. You can't draw every single line in here, but they're still there, right? So the difference between 1.0265 and 1.0270, right? There's 5 more lines in there. There's as many as you want. You guys don't have to go crazy. So I would actually take and draw a line. Draw a new line that intersects with your intersection. All right, and then read that off. And remember, these are kind of going backwards, right? They get higher as you go this way, so don't get tripped up and think, well, this is lower than 1.0265, so it must be less. Well, it's not. All right, it's a little bit more. And this is going to be about 1.0266 grams per centimeter cubed. I sort of told you guys this before. I'm going to keep emphasizing it. Don't forget your units, right? All these problems have multiple points to them. Units are in all of them. I really care about units. So anyhow, that's how you find this. So what have we seen? Now we've seen what density is, how that stratifies different liquids based on their mass or even just temperature. We've seen that water has incredible thermal characteristics that allow it to absorb an incredible amount of heat without changing temperature too much. And we've seen that temperature and salinity affect the density of ocean water. And that is what's going to drive these currents. So you end up with these massive global ocean currents. Again, transferring heat all around the planet, stabilizing our climate, driving plankton, giving them somewhere to go, and that's it for now. So make sure you now have the tools to go and do your first homework. Again, pay really close attention what the problems are saying. If there are multiple points, I'm looking for a lot of stuff in there. Pick all this stuff apart. And most importantly, come to office hours, send me emails if you have questions before the due date. Because once you guys turn it in, I can't really do anything about it. So that's it for now, and stay tuned as we move from thermohaline into surface currents next. I'll see you guys later.